Welcome, this is lecture number 57. In this lecture, we are going to talk about digital control in high frequency switch mode power converter, some introduction and some motivations. So, here we are first going to talk about primary objective in DC power conversion system, then what are the limitation in analog control, and I want to show you using a boost converter case study. Then we need for digital control and some basic building blocks and some introduction of digital voltage mode and current mode control architecture. Since it is not a digital control course, so I want to give some brief introduction in this lecture and the next lecture, so that you get some motivation why to go for digital control, and maybe in future you can think of digital control another course. So, here we are talking about a DC power conversion system, and we have discussed this in lecture number 1, the first lecture. The primary objectives, that means we have a DC source and then we have DC load, and the source voltage can vary, load current can vary, and we have also discussed about dynamic voltage scaling. So, we need to achieve tight voltage regulation, and some cases we need to also regulate the current. Then we need to achieve high efficiency over a wide range, very fast transient response, high power density and small size, and also we need to ensure stability. Now, the question is, what are the control requirement and what are the challenges? So, it can be categorized into two parts. One is the dynamic requirement, another is the static requirement. In the dynamic requirement, we will talk about very fast transient response. That means, the fast transient response is something which is obvious, and we have spent lot of time to achieve this. Initially, we started with small signal model. We have developed design and tuning method to get the whatever performance is achievable within the model limit. Then we also discuss about nonlinear control, then also we have discussed about nonlinear tuning, and we got the fastest response, and we also discuss about another reconfigurable circuit which can even improve the performance. Then we need to reduce the we need to achieve small undershoot overshoot for both current and voltage, and we need to ensure the first scale stability, that means subharmonic stability should not come. There should not be any large signal or small signal stability, because we also talk about large signal stability like Lyapunov stability, and small signal like we have to ensure that it has sufficient stability margin like a phase margin, gain margin, bandwidth and so on. And we also need to achieve low audio susceptibility and low output impedance. In the static requirement, we also discuss about high efficiency, because we need to achieve high efficiency so that the thermal overhead can be reduced, the size of the converter can be reduced, both size can be reduced. Conductor radiated EMI is another important, because though we are not discussing here, there can be active EMI control by means of spectral spreading. We can spread the spectrum by means of periodic modulation, by means of randomized modulation and so on. And we can operate at a higher switching frequency, that is another objective, and that we can use wide band gap devices, and we can reduce the size for high power density, and we also need to achieve very good line and load regulation. So, this requirement, along with this we need some additional requirement for current trends of power supply as well as for the future power supply. Some of this we need to have a reconfigurable controller, because we have discussed we need to tune the controller parameter to get fast transient, because we should come out from the traditional analog control where we if we use the off chip component where we have no flexibility or little flexibility in tuning the controller parameter. As a result, our design was based on the worst case, and that is not going to work to meet the future requirement. So, we need to have a reconfigurable controller, whether we go by small signal based design, whether we go for large signal based tuning or nonlinear control. So, our controller parameter has to be reconfigurable. That means, whether we can use one controller throughout, but update the parameter, or as per requirement we can also change the controller configuration. Suppose if we develop a IC which can be used either in voltage mode configuration or current mode configuration, or we can change the different modulator architecture. At least for voltage and current mode we may need different compensator, or we also discuss that load transient response type 3 may not be good enough, we may go for even lag lead compensator. So, this kind of structure can be incorporated in reconfigurable controller, and that can be easily implemented in digital control. so that we can take the controller that we want, and we can also update the parameter to get fast response. And we can also do a trade off with efficiency, because we saw if we achieve the time optimal response, since we are reducing that, in the previous lecture we saw the time optimal response over the classical response can improve the dynamic efficiency, because the number of switching event during a large recovery is reduced, so that your driver loss can be reduced. So, but in conventional way, not only we are losing performance, we may lose the transient efficiency, or basically energy efficiency. Similarly, we want to go for real time energy optimization, because if we use a fixed dead time for synchronous converter, then we will really lose efficiency, because the dead time will be decided by your load step size as well as your that means load current and the input voltage condition, right. So, if you are operating at a higher load, that means your switch, when it turns off, it will swing from that load current to the zero current. But if the load current is low, then the current magnitude is reduced. So, why do you unnecessarily use a larger dead time? So, you can reduce the dead time. So, you can optimize. We can use the coordinated control, that means we can coordinate between multiple controller, because we discussed that in a smartphone there are multiple POL. We need to coordinate, so that we can use the information, because all the converters, suppose there are load transient, right. So, but you have a one battery, if all the transient are, if we attain all the transient, all the converter undergoes transient, then the battery has to supply huge current, and that battery can collapse. So, this coordinated control can help to reduce. We have to only respond to the transient which are critical, and then slowly we will respond to the other transient. Similarly, we can coordinate between the controller, because if there are multiple converters, there can be interaction, and that can lead to stability problem. And this part is also important for microgrid application and other application, where this coordinated control can really help to overall improve the performance, stability and efficiency. And this can be done by means of communication, because we are talking about PM bus communication, PM bus, and now the products are also available. So, it is a trademark product, a technology where this is a protocol where you can share the data and the clock between multiple converter by this communication. So, this communication also we can go for a more reliable power supply design, we can make the power supply safe, and also we talked about hot swapping multiple controllers. So, by this information exchange we can achieve the hot swapping technique as well. So, this motivates to go for something like a digital control already. So, something like we go for digital control. Another thing, if we take a boost converter that we have discussed multiple times, and if we go for this boost converter, the gate signal we have considered earlier U, here I have taken U. So, Q we have taken earlier, the gate signal. So, you can use this as a Q, this is our Q, Q equal to 1 or 0, discontinuous. So, we generally obtain state space model, which is a discontinuous control, and this thing we have already discussed in the past. Now, suppose if we obtain the large signal model, linear small signal model, then we know how to obtain this transfer function, and this boost converter, then the duty ratio we are going to control, it has a right of plane 0. And if there is a right of plane 0, we have discussed in the earlier lecture, the right of plane 0 introduces a undershoot behavior, right. Because if the converter has no 0, that means if the transfer function has no 0, only 2 pole, and if it is underdamped, so this is the one which is number 1. But suppose if you multiply with a right of plane 0, number 2 transfer function, so this will be, there will be undershoot. So, if the right of plane 0 comes close to the imaginary axis, you will have more and more undershoot behavior like this. So, it will be more, there will be more severe bandwidth problem. So, if we take the open loop transfer function of the boost converter, we have a one right of plane 0 in the control to output transfer function, and that right of plane 0 comes close to the imaginary axis at high load and high voltage gain. So, that makes the bandwidth very slow. Similarly, the limited gain margin leads to smaller closed loop bandwidth. Now, that transfer function also consists of 2 poles which has complex conjugate 0, and that means under high load light load condition you can have a poor damping, and that may reduce your phase margin and leads to more overshoot undershoot. So that means if you take the dynamics of a boost converter, the RH0 limit your high load and high voltage condition, bandwidth limit, light load condition, you have complex conjugate poles. So the pole 0 compensation become very difficult, and we have already discussed this case study using a type 3 compensator, and then fixed gain controller may not be sufficient based on the worst case design, and generally our F control bandwidth is limited to 1/5 of the RH0. So that is why voltage mode control is not preferred for a wide duty ratio operation in analog control. If we go to current mode control, our right half plane 0, we can convert into a first order pole, but the right half plane 0 still exists and it remain unchanged. It does not change the right half plane 0 when you move from voltage mode to current mode, but it gives a single pole approximation of the pole, and we can simply use a type 2 or type 3 compensator. Here we discuss that we can achieve bandwidth up to 1/3 of the RH0. But if we go for fixed gain controller, we will end up the worst case bandwidth to be 1/20th of the switching frequency, and which may not be acceptable. So then the limitation of analog control, if we go for voltage mode control, it is very difficult to compensate under varying load current and input voltage condition. We saw under current mode control, subharmonic oscillation may come when the duty ratio exceed 0.5, we need to compensate ramp, but if the ramp compensation is excess, then the poles become complex conjugate, and then again the problem may come what we saw in the voltage mode control. An analog control using fixed gain, the worst case design of a boost converter can be even 1/30th of the switching frequency, and which is not acceptable. Then what to do? What are the opportunities using digital control? So we can overcome this thing by means of controller tuning, and that we have discussed in the previous lectures, the tuning even the last in week 11, but those tuning can be implemented in digital, right. Dynamic ramp compression, dead time optimization is possible. So these are the some of the reasons that it motivate to go for digital control. If we go to digital control, then in our PWM block we introduce a digital pulse width modulator, DPWM, and in your A to D block you have a A to D conversion where we have a sampler circuit and also a quantizer block. Now the question is how to sample the output voltage, in what rate we should sample. So if we sample higher than switching frequency, then, and since the digital control, the Nyquist frequency is half of the sampling frequency, so that you will find that aliasing effect will come. So then we need to put a low pass filter to attenuate that effect. But if we take one sample per cycle, then in the Nyquist frequency range there is no aliasing effect, so we do not need any low pass filter. So one sample per cycle is a common thumb rule for DC-DC converter. In digital control, the voltage loop is sampled once per cycle. That means it reduces both sampling as well as computation, because even if you sample at a faster rate, the compensator has to compute at the same rate. So that requires a lot of processing capability. So if you reduce the computation requirement, then you can also reduce the power, right. And high frequency DPWM is very much possible. That means if you go for very high frequency, it is possible because the sampling rate is almost same as switching frequency. Now if we take a voltage mode control architecture, so we have an A to D converter here. So output voltage is compared with the reference voltage, and the error voltage, it is a controller, and then we have a digital comparator, and then that actually you have a DPWM block. And there are many architecture of DPWM block, and that we are not going to discuss in this course, because this course I just want to give a brief introduction in digital control and some motivation. And if you draw the waveform of the digital control, we are sampling the output voltage here, but you know that every ADC takes some time to convert, that means the ADC conversion time. So we need to provide some delay where the ADC conversion as well as this controller computation both can be completed. So your actual data which is sampled here will be ready here after computation is a control voltage, and that is compared with the sawtooth waveform, and since it is a digital, it has a staircase kind of waveform. So this will give us this kind of closed loop operation. But the delay can be comparable to switching period, because even if we are taking the delay, we do not want a very high speed ADC, because that also increases cost, because we want to reduce cost. We also do not want a very high speed digital computation, so we need to provide time. And in fact, this delay sometimes we intentionally increase in order to keep some regulatory purpose in mind. And if you go to different digital control architecture, this delay has to be like one sample delay. So the delay can be close to switching period. Now, this digital control, we can reconfigure this controller. We can do real time optimization by means of dead time. We can optimize in this driver circuit. So the whole thing up to this MOSFET, including this MOSFET, and from this ADC, the whole thing can be using a single CMOS circuit, that means CMOS. So you can reduce the size and everything, and you can do very fast prototyping for validation. In like you can use an FPGA based prototyping to validate idea, and you design the code, and you can use your HDL code, hardware descriptive language, and whatever HDL code you synthesize, that HDL code can be used to synthesize your actual digital IC, and then PM bus interface can it will make your power supply reliable, you can communicate and achieve higher performance. But it comes with various price. First of all, you need ADC. First of all, you need, here there is no DAC requirement, but there is a resolution in the ADC as well as the resolution in the DPWM, and that will put a limit on your duty ratio resolution. Duty ratio resolution. Okay, and this duty ratio resolution can, if the DPWM resolution is poor than ADC, the quantized voltage level may not be able to map properly, and it will back and forth map between the successive level. So exact duty ratio may not be achievable, so it cannot lock the error into the zero error bin. Okay, so what is zero error bin? That means if you take qualitatively, this is the quantized error voltage. Okay, and there is a zero limit here, right, and then it goes like this. So within this voltage range, their quantized voltage is 0. So your actual digital controller will see like error voltage, 0 error voltage, but actually it is not 0, because within this voltage range you may have a variation in the error, but as long as within this is called 0 error bin. 0 error bin. So this is 0 error bin. Okay, so you need to lock this error into 0 error bin and keep it there, so that you can achieve the stable periodic behavior. But if you do not do that, if your resolution is poor, then you will end up with this kind of behavior, which may be called as a limit cycle, or it can be more complex nonlinear phenomena. In general, the phenomena can be substantially different, like ordinary limit cycle, and it may end up with your duty ratio saturation. Okay, so there are various necessary sufficient conditions are available, and we will discuss a little bit in the next lecture. There are very highly cited reference that we will discuss in the next lecture, that will lead to this limit cycle oscillation. So, but if you go to, these are voltage mode control, if you go to current mode control, so the current mode control, it is a 2 loop control, and we have a very fast current loop, but a slower voltage loop. So this voltage loop can be kept in the digital domain by putting an ADC here, but after the controller computation, then your peak current reference is coming, and that you can use a D2A converter to generate the analog current reference here. So this is my analog current reference here, and that is directly compared to the sense inductor current, and then the rest of the process is same. And this architecture is called mixed signal, where the current loop is in analog and the voltage loop is in digital, because we want to retain the fast dynamics of the inductor current. We can sample the voltage once per cycle, because it is a very slow dynamics, the ripple is small, but we cannot do for the current, because the current ripple is 20 to 30% of the nominal value. So we must take either in analog, we must take into account the ripple information. So one way you keep the analog voltage current in the analog loop. The another way, we can keep put another ADC to sample the inductor current, but this ADC has to be sampled at much faster rate, so that your Suppose if this is your actual inductor current, and if you take a multi-sample ADC, like it is like this. So, inductor current can be sampled multiple times, it will look somewhat closer to the inductor current. But this multi-sample ADC also have a lot of stability issue, right? Because in the last lecture we want to highlight some of the aspect here. So, a lot of stability issue, and if we use a high sampling rate, then you also need to have a very fast ADC, and power will increase, the cost of the ADC will increase. But this architecture where we keep both voltage and current in digital is called fully digital current mode control. Now, in high frequency then fixed frequency, that means high frequency application, but the controller is fixed frequency, digital current mode control, mixed signal and fully digital. In both cases voltage is in the digital domain and they are sampled at the same rate of the sampling frequency, but in the mixed signal we keep the analog current loop. So, we can retain the fast current dynamics, we can achieve very fast transient response. In fact, whatever tuning we have discussed, we have implemented with using analog current loop, mixed signal current mode, and adaptive ramp compensation is possible to make the system stable. That means, we can use this current mode control for a wide duty ratio operation. And if you look at this, the ramp compensation can be added here from digitally. So, you can add any RAM that you want from the digital platform, digital controller. But it comes with a price, you need an A to D or D to A converter, because if you see it requires a D to A converter here. So, that increases price. Also, high bandwidth current analog comparator, because these comparators are in analog domain. So, the bandwidth of the comparator has to be very high depending upon what is the switching frequency. But in this case the comparator is in digital. Okay. So, if we look at this fully digital cascaded loop, high sampling, higher rate and current loop slope selection. So, now as I said, one way you can either sample multiple time, that is one possibility, or you can sample the current once and that is my sample current, but you can emulate inside the digital loop. And this slope, whatever you are using, it is my slope of the ramp, not the slope, and this is the slope of the current. So, MC need not to be always M1, in fact it may not be. Okay. And actually there are multiple works that even if you set MC, because the initial objective was to get MC equal to M1, but that may not ensure different type of stability, and that we will discuss in the next lecture. So, mixed signal current mode control architecture I told, but in fully digital we can use one sample per cycle, and then we can add a ramp to emulate the current ripple, but the question remains, what should be the right current slope? If you choose higher, lower or equal, whatever is required, that remains also another concern. So, in summary, today we have just discussed the primary objective in DC power supply conversion system. We discussed about limitation of analog control and we have taken one boost converter case study. We discussed need for digital control and some basic building blocks, but this is just an introductory talk. Maybe in next lecture I will give a little bit more overview, but again this course is not designed for digital control. So, we are not going too much about digital control. Then we have also discussed some digital voltage mode and current mode control architectures. So, with this I want to finish it here. Thank you very much.